Now, there's one last thing to talk about in this segment, which is called projection. Projection. And for that, we'll need to draw a triangle. So if I've got a vector r and another vector s, now, if I take a little right-handed triangle, drop a little right-handed triangle down here, where this angle's 90 degrees, then I can do the following. If I can say that, if this angle here is theta, that cos theta is equal to, from SOHCAHTOA, is equal to the adjacent length here over the hypotenuse there. Adjacent over the hypotenuse. That is, and this hypotenuse is the size of S. So that's the adjacent over the size of S there. Now, if I compare that to the definition of the dot product, I can say that R dotted with, we'll have fun with colours, dotted with S is equal to mod R, size of R, times the size of S, times cos theta. Cos theta. But the size of S times cos theta, if I put S up here, I just need to put my theta in there. Cos theta is just that adjacent side. So that's just that adjacent side here in the triangle. So the adjacent side here is just kind of the shadow. If I had light coming down from here, it's the shadow of S on R, that length there. It's kind of a shadow cast if I had a light at 90 degrees to R shining down on S. And that's called the projection. So what the dot product gives us is it gives us the projection here of S onto R times the size of R. One thing to notice here is that if S was perpendicular to R, if S was pointing this way, it would have no shadow. That is, if cos theta was 90 degrees, that shadow would be 0. The cos theta would be 0 here, and I get no projection. The other thing the dot product gives us is it gives us the size of R times some idea about the projection of S onto R, the shadow of S onto R. So if I divide the dot product R dot S by the length of R, just bring the R down here, I get mod S cos theta. I get that adjacent side. I get a number which is called, because R dot S is a number and the size of R is a number, and that's called the scalar projection. And that's why the dot product is also called the projection product, because it takes the projection of one vector onto another. We just have to divide by the length of R. And if R happened to be a unit vector, or one of the vectors we use to define the space of length 1, then that would be of length 1, and R dot S would just be the scalar projection of S onto that R, that vector defining the axes or whatever it was. Now, if I want to remember to encode something about R, which way R was going, into the dot product or into the product, I could define something called the vector projection. And that's defined to be R dot S over mod R dotted with itself, so R dot R mod R squared. So that's R dot S over R dot R, if you like, because mod R squared is equal to R dot R. And we multiply that by the vector R itself. So that dot product's just a number, these sizes are just a number, and R itself is a vector. So what we've done here is we've taken the scalar projection R dot S over R, this guy, That's how much S goes along R, and we've multiplied it by R divided by its length. So we've multiplied it by a vector going the direction of R, but that's been normalized to have a length 1. So that vector projection is a number times a unit vector that goes in the direction of R. So if R, say, was some number of lengths, the vector, that would be R divided by its size, say, if that was a unit length vector I've just drawn there. And the vector projection would be that number S dot R, that adjacent side, times a vector going in the unit length of R. So that's, if you like, the scalar projection also encoded with something about the direction of R, just a unit vector going in the direction of R. So we've defined a scalar projection here, and we've defined a vector projection there. So, good job. This was really the core video for this week. We've done some real work here. We've found the size of a vector, and we've defined the dot or projection product. We've then found out some mathematical operations we can do with the dot product. That it's distributive over vector addition and associative with scalar multiplication, and that it's commutative. We've then found that it finds the angle between two vectors, the extent to which they go in the same direction. And then it finds the projection of one vector onto another. That's kind of how one vector will collapse onto another, which is what we'll explore in the next 2 videos. So, good work. Now's a good time to pause and try some examples that put all this together and give it all a workout and a bit of a try before we move on.